Yeah, thank you, everyone. So we'll get started with the first presentation of the afternoon. This presentation is led by Shorya Awtar, Professor of Mechanical Engineering at the University of Michigan, Ann Arbor. His research interests include mechanical design, human-centric design, mechatronic systems, and robotics. He has developed affordable medical devices for minimally invasive surgery, precision motion stages for semiconductor metrology, motion sickness mitigation solutions for autonomous vehicles, and micro-electromechanical systems, actuators. Prior to joining UM, he worked at the General Electric Global Research Center and the National Institute of Standards and Technology. Professor Awtar earned his mechanical engineering degrees from the Indian Institute of Technology, Kanpur, and the Massachusetts Institute of Technology. He has published more than 80 peer-reviewed conferences and journal articles and has 36 inventions that are either patented or patent pending. Professor Awtar has started 2 companies, FlexDeck Surgical and HyperNap, to commercialize the technologies developed in his research lab. He has received the Leonardo da Vinci Award and Thomas A. Edison Patent Award from the American Society of Mechanical Engineers, the Gold Award for the Translational Research from the American Society of Biomechanics, multiple R&D 100 awards, and several Best Paper awards for his research, innovations, technology transfer, and societal impact. Professor Awtar is a fellow of the ASME. He teaches graduate and undergraduate courses as well as professional tutorials in machine design, mechanism design, and mechatronic systems. He has also worked with the Ann Arbor Hands-On Museum to create educational exhibits for K-12 children. Today's presentation is titled Motion Sickness Alleviation in AVs via Preemptive Interventions. This talk presents the PREACT system, a new technology for alleviating motion sickness in AVs. PREACT employs prediction algorithms to anticipate impending inertial events associated with driving and accordingly makes preemptive interventions via active seats, restraints, and passenger stimuli before the inertial events actually happen, thereby averting motion sickness. The CCAT researcher will present the development of several components of this technology so far and their plans for experimental validation via human subject testing at the M-City facility. Without any further ado, Professor Shorya Awtar.
So thanks everyone for being here. This seems like the I think, slide should be working. The post-lunch session, I'm going to try hard to not put you all to sleep. It looks like some people might be joining by Zoom as well. So once again, thank you to everyone who's attending this talk. What I'm going to talk about here is motion sickness alleviation in AVs, in autonomous vehicles, via preemptive interventions. This is a new idea that we have been developing for the last few years. It's called PREACT. What I'll show is the background behind the idea, the genesis, what the concept is, the various technology modules and components, and leading all the way to experimental testing that's going on right now. So I won't have any experimental results to present, but I'll tell you what the technology is and what its objectives are. The team that I'm working with includes 2 outstanding graduate students, Nishant Jalgaonkar and Daniel Schulman. Part of my team, collaborative team, is also Dr. Monica Jones from UMTRI and Professor Bernard Martin, who is a professor at the IOE department at the University of Michigan. Now, a key thing here, we're all attending the CCAT Symposium. I think we all believe in the value of connected autonomous vehicles, but also not just connected and autonomous vehicles, it's also electric and shared, right? So ACES technologies, and there are numerous advantages of these technologies. I think an obvious one is fewer road accidents, reduce injuries and fatalities. I think the number is, the metric that is often used is 38,000 fatalities in the US alone every year, more than 4 million injuries in the US alone, and more than 90% of these, there's something goofy going on with my slides. This is moving on its own. Let me try. Okay, let me try something. Okay. more than 4 million injuries, and 90% of these are because of driver error. And again, that's something that autonomous vehicles can potentially address. There's also a significant amount of wasted time that people spend while commuting. In fact, the estimates are more than 70 billion hours in US alone are spent by people just sitting in cars. Part of it is the commute to and back from work. Oh, I don't know why this is just moving on its own.
So you just gotta be careful where you at.
Yeah. I need something built into this by mistake. Okay, well, I'll be careful. Again, so there's this loss in productivity. In fact, Morgan Stanley estimates that loss in productivity is close to $500 billion. With ACES technologies, there's also the promise of lower environmental footprint. About 17% of fuel consumption and 14% of energy consumption in the US is a result of automobiles, and that also can potentially be reduced via ACES. And finally, mobility as a service can enable a more equitable access to transportation. Right now, about 9% US households cannot afford access to a vehicle. So these are all promises, but with all these promises, there is a catch. Okay? And the catch is this, that, avoiding, the fact that you're sitting in an autonomous vehicle increases the chances of motion sickness. And this is like more than a dozen articles that have demonstrated this, that have talked about this. And a big question that now is being raised is, will the motion sickness, the level of discomfort, be so much that will impact the adoption of these really promising technologies, such as autonomous vehicles? There's in fact some very thorough studies that have been done here at the University of Michigan by one of my collaborators, Dr. Monica Jones, again, that has demonstrated over and over that in autonomous vehicles, the passengers will be more prone to motion sickness. Now that raises an interesting question. Why does motion sickness happen? And there are numerous theories around this. And the theories, again, let me see if this is going to work. The theories all are based around the idea of recognizing that there's several inputs, sensory inputs for any individual. These include the ocular input, the eyes, the vestibular, which includes otolith organs and semicircular canals, and then there's proprioceptive systems. All of these systems somehow take input from the environment and produce a perception that leads to motion sickness. And in between, there are many different models that people have created to try to understand why this, incidence of motion sickness happens. Oftentimes, this is reflected in what's called the sensory conflict theory, where information that is being received from two different sensory organs, it conflicts. So, for example, if you're just sitting and you have a visual input, and the visual input is like a spinning image, while in reality, you are just still, which means your vestibular organs don't sense any motion, but your ocular organs, eyes, sense motion. And that conflict between the two leads to motion sickness. Again, there's many different flavors of this conflict theory. There's a subjective vertical conflict theory. There's a velocity storage theory. In all these instances, it is what a human is perceiving through their various sensory organs, and also what they think should be happening. A conflict between the two leads to motion sickness. This is an area of academic research, but more importantly, I want to present to you some empirical data. Okay, that empirical data is simply that anyone who sat in a car probably has this experience that the driver is always less motion sick than the passenger, right? Is that anyone, maybe show of hand, right? Does anyone know why that happens? Driver is, right? So there's an interesting thing. So for example, consider this scenario where a car is moving, a driver is driving a car, just a traditional car. And the driver, let's say, takes a right turn. Okay, the driver takes a right turn. As a result of the right turn, centrifugal effect causes the car to tilt to the left, and also the passenger, right? I mean, if you're a passenger sitting in a car and the car takes a right turn, the passenger is going to tilt to the left because of centrifugal effect. In fact, that happens to every passenger, with the exception of one person. And that one person is the driver. That driver, because they know, because they have the anticipation that I turned the car, they have the anticipation of what's about to happen. They know when the car turns to the right, there'll be centrifugal forces that will throw everyone to the left. Knowing that, they intentionally lean their body into the turn. So here's just a thought exercise. Next time you're driving, and if you're a driver and you're taking a right turn, notice that you yourself, it's something that's implicitly happening inside your brain. You don't think too much about it, but when you are taking a turn, you will forcefully lean your body slightly into the turn, versus anyone else in the car gets thrown to the left. So it's that difference that makes a difference also in the outcome of motion sickness. And anyone who has kids or who drives a minivan, you'll know that the passenger who sits next to you, they probably have a little bit of an idea of what's going on, but the person behind you, or in a minivan, the people who are sitting in the very last row, right, the little kids, they are the ones who get the most motion sick because they don't have a clue what's going on, okay? So the key idea here is there is a combination of two things. There's anticipation, right? The driver knows what's about to happen, but that's not enough. They know what's about to happen and they do something about it, right? Another thing to notice is, for example, if you're in a car and the car, someone hits brakes and the car decelerates, all the passengers are going to get thrown forward, okay? But if you're the driver who hit the brakes, then as a driver, you know what's going to happen. And oftentimes the driver then leans against the steering wheel. Just they brace their body just slightly because they know that their body is going to be swung because of this inertial event that's about to happen. Okay, so this idea of anticipation and preemption has been known. It has been investigated quite a bit. And it has been shown that once you have anticipation, motion sickness goes down. And we have anecdotal evidence, just looking at our own experiences, but there are also formal studies that have demonstrated this. Now, why is it that we worry about motion sickness? There's a certain significance to it, and that is 1 in 3 adults. 1 in 3 adults is prone to motion sickness, and in certain age groups, that incidence can be higher. Okay, and certain age groups, especially young children, the incidence of motion sickness can be higher. Again, certain demographics, the incidence of motion sickness can be higher. Now, right now, we think of motion sickness as a nuisance. I mean, it's not something that is assumed to be an impediment to transportation or anything like that. The reason for that is that currently, the average occupancy of a vehicle in the US is 1.5, right? Out of that 1.5, who's the one? That's the driver, right? That's the driver, which means that most vehicles in the US are driven by, or they have, close to one occupant. Here's another data. That was a DOT data. Here's a Department of Energy transportation data book that shows that 3/4 of commuters in the US, they commute alone. Okay, so the majority of people in vehicles right now are the drivers. Now imagine a future where you have autonomous driving. Now in autonomous driving, there is no driver and everyone is a passenger. And because of that likelihood, because of that impending future, there's now the concern that there will be a higher incidence of motion sickness, which can potentially lead to an impediment in the adoption of these amazing technologies. Right? I showed on the first slide how autonomous driving can potentially cut down fatalities and accidents and injuries and so on. It can give us back productive time. It can provide access to transportation and whatnot. But if, as a society as a whole, we're sitting in these vehicles and we're throwing up, then it's not a technology that'll be very attractive. And that's what makes addressing motion sickness in autonomous vehicles an important area of investigation. So what are the existing solutions? Again, anyone who has little kids probably has looked through all of these solutions. pharmaceuticals, right? One is pharmaceuticals. So this is Dramamine. And Dramamine is, it's over the counter. It's really not a solution. It's something that is addressing the symptom. It really knocks you out, makes you drowsy and sleepy. So if on one hand you're trying to reclaim productive time, you don't want to take a Dramamine and go to work. I mean, you'll have a pretty bad day. I mean, there's all kinds of side effects associated with Dramamine. There's an even stronger pharmaceutical, and you notice this is RX only. It's often used in the military and has even stronger side effects. So not quite the solution that we're looking for. There's also acupressure bands. I mean, I have, with the exception of this, everything here I have at home because my kids are very motion sick. I can tell you by personal experience, this is a waste of money, at least in my case. There are these acupressure bands and whatnot, but the effectiveness is completely not proven. Then another key aspect is in the military, they make use of behavioral methods and habituation. So one of the things about motion sickness is if you can eventually habituate a person, and that's why older people are less motion sick than younger people, because younger kids are still trying to habituate to the sort of conflict that can exist. Okay. Other solutions, so these are like the current solutions, other solutions that are being explored, those include a whole bunch of things. So at the vehicle level, there's route planning. You can take a path that involves fewer turns, fewer acceleration, fewer deceleration. You can actually monitor the driving profile. Again, perhaps you've sitting with a friend who's a herky-jerky driver and you get all the more dizzy, versus if you sit with someone who drives a bit more softly, you get less motion sick. And those ideal or optimal driving profiles can be programmed into autonomous vehicles. So that's a technology that has been recognized. Vehicle suspension, there's a lot of thought about how can you make the suspension more and more comfortable. Unfortunately, suspension doesn't do too much about lateral acceleration that happens when you're taking a right turn or left turn. It doesn't do much about longitudinal acceleration when you're accelerating or suddenly braking. Then there's cabin level mitigation measures. So people use passive seats, active seats. Like passive seat is, imagine a seat that is mounted on a gimbal, and if you have too much roll, pitch, yaw, the seat will just react to it. Active seats have all kinds of actuators built into the active seats. Again, none of these work. By the way, none of these make use of anticipation. They're all reactive technologies. None of them make use of anticipation. They operate only when an event has happened or after an event has happened, not ahead of time. Then there's also, managing the cabin temperature, lights, scents, and so on. There's passenger level mitigation. So huge amount of technologies here that are being developed in the form of visual information. So VR, AR type of headsets that are being developed to provide visual inputs. And that is, again, a space where people are just throwing stuff at the wall to see what sticks. There's no known solution so far. More aggressive, more ambitious people have tried neural implants that you literally implant certain devices around your otolith organs to sort of scramble the signals that the otolith organs are sending to your brain. As much as I hate motion sickness, for sure I don't want anything implanted in my brain to address this issue. So while so many, these are dozens and dozens of papers and patents, perhaps, at least we have tracked close to 100 papers and patents that try to attempt motion sickness mitigation. There's not one result to our knowledge that definitely shows any meaningful outcomes. What is interesting is none of these ideas seem to be learning or leveraging what we know works in the case of a human driver. Okay? So that is the combination of anticipation and preemption. So the idea behind PREACT technology is to recreate the anticipation by virtue of predictions and recreate the preemption by virtue of a bunch of other hardware technologies. So I'll show you. The anticipation is based on the significant amount of data that already exists, right? So even right now, you can imagine if I put in Google directions to go from here to the airport, Google Directions will tell me with a very high degree of accuracy how long it'll take. It'll tell me the path that I'm going to take. Now add to that more data related to the radius of curvature at a particular right turn. Add to that the velocity at a right turn. Add to that the vehicle dynamics, the suspension of a vehicle. Include in that the data related to a person, their size, height, weight, CG, and things like that. If you were to take all of those pieces of information, you can predict with a very, very high degree of accuracy, either using deterministic models or machine learning algorithms that are data-driven models, to predict what's about to happen. In fact, that prediction can be far stronger and far more effective than the anticipation of a human driver, right? What we can do via a computer program and a software, that can be far more powerful in terms of prediction and anticipation compared to what a single human does themselves. But that's only one part of it. The second part of it is, once you've made this prediction, you have to do something about it. And that doing something about it is the preemptive hardware. So what we do in the PREACT technology is, in an autonomous vehicle, all the seats, we equip those seats with an active tip-tilt seat, right? And what that active tip-tilt seat does is, imagine the vehicle is approaching a right turn. Based on the prediction, you know that a turn is coming up. Before the turn comes up, it's a right turn. So if you didn't do anything about it, then all the passengers would get thrown to the left, and the otolith organs will pick up, that there's a conflict going on, and that'll lead to motion sickness. To mitigate that, what we do is, even before the turn has actually happened, the active seats start to tilt into the direction of the turn. They start tilting into the direction of the turn, so that when the turn happens, the weight of the passenger, that weight itself contributes to the centripetal acceleration, and the body doesn't get thrown to the left, right? So you do this gradually and gently, ahead of time, slightly ahead of time. In fact, that's only an active seat. You can also have a multi-point active restraint. And that active restraint is, again, for example, a right turn is approaching. The active restraint, the seat belt, will start tugging the passenger into the direction of the turn. We also have active passenger stimuli, and that could include a bunch of vibrotactile motors, these haptic motors, the vibrating motors that are embedded into the seat, that give a cue, give a little bit of an idea to the passenger that something's about to happen, and you can tilt your body in response to that. So it's this combination of anticipation and preemption, which is what the PREACT technology is. And again, this animation that I showed earlier, this is a vehicle with a traditional vehicle, human driver, versus on the right, I'm going to show a vehicle that is an autonomous vehicle with no human driver. The vehicle takes a right turn. The active seats lean into the turn slightly ahead of time, and thereby eliminating the sensory conflict, and thereby leading to a happy outcome. Okay, so that's the PREACT idea. And PREACT, the name, is inspired by anyone who's watched Minority Report? Tom Cruise? No Tom Cruise fans? Yeah, there you go, Calvin, right there in the back. If you recall Minority Report, there's the concept of precogs. There's three people who are able to predict the future, that a crime is about to happen, and then Tom Cruise, of course, shows up to prevent the crime before the crime has happened. So that's the PREACT idea. Instead of reacting to an event, you are pre-acting. You first make a prediction and you do something about it. So here's a bit more detail about what the technology is, but just real quick, Calvin, how am I doing on time? Am I halfway in or 30 minutes left? Okay. Okay. So this shows the PREACT system in its full glory. It has 3 levels of computation involved. There's a certain data center. These are vehicle-level algorithms, and this is vehicle-level mechatronic modules. So anything that you see that is not captured by a red boundary, that is the architecture of an AV in any case. Like a current AV will have that kind of an architecture. You will have a whole bunch of data that informs vehicles' self-driving algorithms, right? Based on this data on traffic pattern and road infrastructure in vehicle dynamics, in a traditional or in a currently envisioned autonomous vehicle, the self-driving algorithm will come up with the route planning and navigation, will determine the control law, the commands that should be sent to the steering system of the vehicle or the acceleration system of the vehicle or the braking of the vehicle and so on. Those commands are sent to those actual hardware systems that are within the vehicle, and then the vehicle goes about and navigates. In case of PREACT, we add another layer to all of this. In addition to the existing data categories, you also include data related to all the PREACT modules, like the active seat, the active restraint, the passenger stimuli. You also include data about the passenger. And based on that, you use all of that data. In addition to the self-driving algorithm, you also have a PREACT algorithm that predicts the inertial events that are coming up and the resulting motion sickness that those inertial events will lead to. Based on that prediction, this algorithm also determines the preemptive commands that should be sent, right? And then it sends those preemptive commands to an active seat, which is mounted within the vehicle, to an active restraint that is integrated with the active seat, to the bunch of passenger stimuli. And these stimuli are, it could be a visual stimuli. It could be, for example, a screen in front of the passenger that indicates that, hey, a right turn is coming up. It could be an audio stimuli. It could be telling a person that in 2 seconds there's a right turn coming up. Or it could be a vibrotactile stimuli. So that's the overall PREACT system implemented in its full glory. What we're doing in this project right now is a very early stage proof of concept demonstration of this technology, and we're working on that as we speak. This just shows a quick comparison of the existing technologies versus what PREACT accomplishes. So what I'm listing here is, this is prediction, this is preemption, and then the degree of intervention. Like, if you are going to preempt, what are the things that you want to do? Will you work with a seat? Will you work with a restraint? Will you work with visual stimuli and so on? So of those, the existing technologies truly lack the prediction component, except, of course, companies like Google, Waymo, Uber, they do a really good job of the prediction, but then they don't do that much preemption. With the PREACT technology, we're doing prediction, preemption, and a rich combination of the interventions that we provide. So that said, this is sort of the value ecosystem that we're working with. We've talked to now close to 40 industry stakeholders, and in that, let's see if this works. Yeah. So of these 40 stakeholders, this includes tech companies that are getting into the transportation space, automotive suppliers. PREACT technology, because of its software component, fits here, the hardware component fits there, but ultimately caters to the automotive OEMs. But the ultimate customer are the passengers and the riders. Also, customers could be mobility as a service companies. Secondary beneficiaries would be, the employees of these people who are riding, PREACT-equipped vehicle, because the passenger will be more productive or will show up at work more refreshed as opposed to being tired and drowsy. Secondary beneficiaries could be insurance companies because of the reduced number of healthcare issues or accidents or fatalities and so on associated with vehicles. So in all of this interaction, a key desire that has come up with industry stakeholders is obviously they want to see some kind of a proof of concept deployment, which is what the project that I'm leading has been focused on, that we are working hard to demonstrate that proof of concept. And our objective is that we want to experimentally demonstrate. Let me see if I can do this. Yeah, we want to experimentally demonstrate the efficacy of the system in mitigating motion sickness under realistic driving conditions using human subjects. That is the gold standard of proving something like this. That said, while the idea of anticipation, preemption has been explored, a key thing that we are investigating is the time horizon of preemptive interventions. Remember how I said with the software, predictive software, we can do a very strong prediction, not just what's going to happen in the next 5 seconds, but also what's going to happen in the next 10 minutes or next half an hour, right? So increasing the time horizon of preemption is a key thing that we are looking at. We're also looking at the cognitive burden associated with these interventions and the influence on productive tasks. So, for example, if there's a visual stimuli that tells the passenger that, oh, a right turn is coming up or a left turn is coming up, how much of a cognitive burden is that on the passenger? And if they're trying to type an email or they're trying to, work on certain slides or something, how much of a distraction is that? Versus if you have an active seat, the active seat doesn't ask anything of the passenger. The active seat just tilts by the right amount, very gently and in a subtle manner, that the passenger doesn't have to do anything. The cognitive burden is low. But at the same time, if your seat is moving a little bit underneath you, that can cause a little bit of a surprise. So those are the kind of things that we're exploring in our current investigation. Here, there's also the likelihood that there may be a certain combination. Right? There may be a combination of the active seat, active restraint, active passenger stimuli that you sort of gel together. You have a little bit of component of each of these and see which combination works the best and which is the least intrusive. What is the dosage, right? For example, if a right turn is coming up and PREACT system says, well, let's make the seat tilt into the right turn. Should that tilt be 5 degrees or 10 degrees or 15 degrees? What should be the dosage of this preemption? Okay? So those are the kind of research questions we're tackling. This is just a very thorough design of experiments that we have planned, and these experiments are just starting now. We are looking at human subject testing, and that human subject testing first will determine which is the optimum passenger stimuli between audio, visual, and haptic feedback. What is the optimum preemption time? 2 seconds, 5 seconds, 10 seconds. What is the effect of preemptive applied active passenger stimuli on productivity? Similar tests are planned for active restraint, similar for active seats, and then various combinations of these. So in all of these, the independent variables that we'll have is, for example, in this case, we'll just use a different kind of passenger stimuli. In other instances, we are varying the level of preemption. The outputs in all of these cases are the reported motion sickness by the passenger, both on a quantitative scale as well as a qualitative scale. But in addition to that, we are also extensively measuring the physiological states of the passenger. We're also measuring the kinematic states of the passenger, like how much is the head tilting, how much is the torso tilting, how much is the vehicle itself rolling, pitching, and moving in roll, pitch, and yaw, and so on. So that's the extensive set of instrumentation that is planned in these experiments. Now, to accomplish this, we have built an experimental test bed vehicle that you see here. This is a Dodge ProMaster van, and we have taken the cargo space that you see in the back and converted that into a lab on wheels. And the purpose is to emulate. We don't have a real autonomous vehicle. We don't have a true AV, but we're going to emulate an AV environment where there will be a human driver and a researcher sitting in the front, but the experience for the passenger in the back would be as though they're riding an autonomous vehicle. We have done all kinds of things like, there's paneling, there's lighting, there's auxiliary power, there's an instrument cabinet here, with a desktop computer. But a key aspect of this is having an active seat. This is a tip tilt seat that is mounted inside of the van, right there. And this is the seat that we intend to preemptively actuate as this van is being driven around. The reason for roll motion, like side-to-side motion, is when there's a right turn or a left turn, because that leads to lateral acceleration. And the reason for the pitch motion, like the lean back or lean forward, that's tied to longitudinal acceleration. So, for example, if the van is going to decelerate, like there's a sudden stop that is coming up, if you didn't do anything, then the passenger, as a result of that braking, will get thrown to the forward a little bit, right? But what we'll do now is, if a braking event is coming up, then slightly ahead of time, we will start leaning the seat backward just a little bit, perhaps 2 degrees, perhaps 5 degrees. And that way we'll minimize the lunging action of the passenger associated with the braking event, right? So those are the degrees of freedom in the active seat. We have done quite a bit of work in creating this profile. This is showing, for example, the roll profile, right? You see this roll profile. Down here is an acceleration event that is, that's happening. It goes from 0 acceleration to about 2.5 or 3 meter per second square acceleration. This is like you're taking a turn. And what this shows is that even before the turn has started, we start commanding the active seat, maybe in this instance, 7 seconds ahead of time. We start commanding the seat to tilt. And the peak happens at the same time, like the peak tilt happens at the same time as the peak acceleration. And then gradually, when the acceleration fades out, the active seat also comes back to its nominal condition. And again, we're looking at many different levels of preemption. Here is just a quick description of the vibrotactile motors that we have embedded within our seat. So these vibrotactile motors, it's exactly the kind of vibrating motor that's in a phone, right? I mean, your phone has a vibrator mode. It's an eccentric rotary motor that you see on the left-hand side. There's another kind of motor, it's called a button motor. We have looked at both of these, and we're working with the eccentric rotating mass motor. And the idea is that if you are sitting on a seat and we have embedded these motors, let's say right underneath the thighs, right? And if the motor under the right thigh vibrates, that is a message that a right turn is coming up. If a motor on the left thigh vibrates, it indicates that a left turn is coming up. In fact, we have 4 motors that you see, right bottom, left bottom, right center, left center, and so on. So the combination of these 4 motors then convey a message to the passenger about right turn, left turn, braking, and acceleration. So these are designed to be intuitive, that the pattern of a vibration is designed to be intuitive, that the passenger recognizes right away what's about to happen. These are the drivers that are used for these motors. These are just H-bridge drivers, very common drivers. There's extensive passenger instrumentation that we have. So the passenger instrumentation includes a bunch of headbed sensors. These are IMUs on the head to measure the roll, pitch, yaw of just the head. Similarly, there are sensors on the chest. Again, a bunch of IMUs. Physiological states are being measured using this Empatica sensor. It's sort of a watch that gives you skin temperature, perspiration rate, and heart rate. In fact, there's more. This is an Aruco marker. That Aruco marker is mounted on the head, and it measures the yaw rotation of the head. Okay? There's a camera that points vertically downwards. This just shows all of that instrumentation altogether. On the right here, this is an SEMG, a surface EMG that measures muscle motion and, in fact, or muscle activity. So you see that's a sensor mounted here. That's an SCM muscle. That muscle dictates or controls the rotation of the head. So if you can detect muscle activity, you can tell that the head is rotating one way or the other. So in fact, there are 4 of those SEMG sensors that are mounted. So these are all IMUs. That's the Empatica watch. That's the SEMG. All of these are laid out in a very sophisticated network of computational devices that are meant for data acquisition. So these are Arduino. So this is the onboard desktop computer connected to 3 Arduinos. Each Arduino via a multiplexer is connected to multiple IMUs. Again, this Arduino via that multiplexer connected to 4 IMUs. That Arduino via that multiplexer connected to 2 IMUs. Additionally, what's not shown here are a bunch of speakers, microphones, cameras. Here's a GPS sensor along with a GPS antenna, right? This is a GPS antenna that does extensive data acquisition and getting this data in a reliable manner that is synchronized with respect to time, again, is a huge logistics exercise that we have now resolved. So like I already showed, it uses an Arduino. Communication happens via an I2C bus. All data is acquired within the MATLAB environment, and that's where the data is also processed. Then, once you have all this data acquisition, the tests are being run in MCity. And in MCity, what we've done is we've created this path, the driving path, that emulates a combination of city and highway driving. And this is based on naturalistic driving data that has already been done by or produced by UMTRI, in fact, by Jim Sayer, who some of you might have met during the symposium. And using that, we've created a path that has a bunch of inertial events, like a bunch of stop turns, stop events, left turns, right turns. We have also, again, these naturalistic driving profiles. We have set the maximum longitudinal acceleration to be 2 meters per second square, lateral acceleration to be 4 meters per second square. And the path has been designed to be able to accommodate anywhere from 3 to 15 seconds of preemption. Okay. So this is a key part of our experimental work. We also have come up with an automatic triggering algorithm. Remember, this is anticipatory action, right? This is preemptive action. So this is an example of where a vehicle, as the vehicle is approaching a right turn, there's an automatic triggering that happens. So first, when the vehicle is out here, there's nothing to do because you're too far from the event, the inertial event. But around the inertial event, this red box that you see, this is a geofence. This is a boundary of GPS location. So once you enter the geofence, now you can tell, okay, the event is approaching, the right turn is approaching. Based on GPS data, you know the position of the vehicle and you know the velocity of the vehicle. Those two things, as well as based on historical driving patterns, like how much time does the driver accelerate or decelerate in going from here to there, you know when you hear how much further is the start of the right turn. Like in terms of time, is it 10 seconds away? Is it 7 seconds away? Is it 15 seconds away? Once you know that time, you can then initiate the preemptive algorithm or the preemptive triggering of, let's say, the active seat. In this case, you'd use, an active seat. So you can trigger the active seat preemptively at the right time. And once the event is done, once the event happens and you get out of this geofence, then you work to bring the active seat back to its nominal condition. So this is the automatic triggering that we've already built and tested. Because this involves human subject testing, so we've also gone ahead and created a very thorough human subject testing protocol. Remember, I showed you that table of design of experiments. So those experiments are being conducted using this IRB-approved study, and this ensures safety for everyone involved. So this is all the planning, preparation, testing that we have done so far. The immediate next goal is to develop and integrate all these modules that I showed you into an operational technology, and then validate. So the first part of this is now done. We have developed and integrated all of these. What we're doing right now is we're validating the motion sickness mitigation efficacy via human subjects under realistic driving conditions in MCity. So that is ongoing. And what is also ongoing is we continue to work with our industry partners to discuss the need for something like this, to understand the need for something like this, to discuss the experiments that we're planning and conducting. So that ultimately our goal is when we can prove this technology, we would like to integrate it within an existing AV platform and bring and translate the technology and bring it to societal use. So that's my last slide. Thanks a lot. And again, I hope I didn't put you to sleep or I didn't make you motion sick, but I can answer any questions. Anyone who might be on Zoom can answer questions. Yes, please.
Purdue.
This is Yun Chang from Purdue University. I'm in the experiment design, in your experiment number 10, I think you mentioned the prediction algorithms. I just wondering, is your prediction algorithm for the human motion prediction or vehicle motion prediction, or which kind of prediction task you are conducting?
First of all, kudos for noticing that detail on that slide. There's many different levels of prediction here. To initially prove out the technology, we are working within a closed environment like MCity. MCity is not like an open urban environment. It just simulates an urban environment. So there we know exactly ahead of time what's going to happen. So the prediction there is more along the lines of this automatic triggering that I shown. Okay, and that is not like in the open world prediction. Open world prediction would be that right now you say, well, I'm going from here to the Detroit airport, right? So that we're not incorporating just yet. Initially, we want to simply show that if you could predict accurately, and based on the prediction, if you were to make a preemptive correction, will it reduce motion sickness, right? That is the first thing we're trying to prove. The element of machine learning based prediction that takes 4 or 5 different streams of data, that is the second stage of our development. Please, yeah. Yeah. So we are hoping in our experiment. So one thing, for example, is if there's a right turn that's going to happen half an hour from now, there's no point in doing anything about it right now, right? It really is the human attention time. That human attention is really relevant for a few seconds. And therefore, our current range of experimentation is a few seconds, like 2 or 3 seconds, all the way to 15 seconds. And the only reason we're looking at 15 seconds is, let's say a right turn is coming up, and it's a really aggressive right turn, which means that I want to move my seat by a pretty large amount, let's say 10 degrees. The reason we want this long horizon of 15 seconds is to give it sufficient time that the tilting of the seat happens gradually enough that it doesn't startle the passenger, it doesn't scare the passenger. Now, as far as the algorithm, so that's the preemption part. As far as the prediction algorithm is concerned, that's a moving horizon prediction algorithm, right? So if right now, I think I can predict very accurately what's going to happen half an hour from now in the context of driving, maybe with 95% accuracy. But what's going to happen 15 seconds from now, that I can predict with 99.9% accuracy, right? So the goal is to keep this moving window that I will make a prediction of half an hour. I won't do anything about it. But when I'm 15 seconds from that half an hour event, that's when I'll have a greater confidence, and that's when I will have my preemption triggered. Okay. Yes.
Interesting presentation. Sorry, I missed the beginning of it. The question is, I think he was kind of going towards the same direction. So you said that you have not fully proven the algorithm that will predict the motion sickness. Am I correct?
That is correct, yes.
Okay. But you have a kind of like a prototype algorithm which you are going to test in the test track.
That's
so I'm
right.
just curious, I mean, I'm sure maybe some stuff is proprietary you don't want to talk about, but what are the things you're looking at in general? Like, is it primarily physiological things, or also information like if the car already has a destination, then you know the mapping information? So what kind of things are you looking at?
So the project is sort of, it's divided into 2 sections, and maybe this is a bit too much information, but the 2 parts of the project is, first, if I, for a moment, assume that prediction is available, right? If, let's say, 100% accurate prediction was available, then could you use that to do preemption, and will that reduce motion sickness, right? That's the first question to answer, because even if prediction was 100% accurate and preemption doesn't fix motion sickness, then the entire point is moot, right? So that's the first set of testing that we're doing in MCity, right? But then once we prove that indeed, with good prediction, if you preempt, and let's figure out whether it's 2-second preemption, 10-second preemption, what combination of preemption, should it be active seat, active restraint, seat belts, passenger stimuli? If we prove that, then we're back to the drawing board to now start looking at what is the best prediction algorithm we can create. And in that prediction algorithm, we want to use information, both real-time measurement as well as historical information, right? So again, back to the example of going from here to the airport, I can, based on what's going on right now with the real-time data that's available versus historical data, I can tell what's the path that's going to be. Right? You can tell what's the path going to be, and as you start executing on the path, let's say all of a sudden, even though I predicted a path right now for the next half an hour, but 15 minutes later, an accident happens on the road, right? So things get rerouted. So as things get rerouted, that data then trickles through the vehicle self-driving algorithm because the vehicle navigation is going to change. And by the same token, it will trickle through the motion sickness prediction algorithm also because now the vehicle path has changed. Exactly. Right? And this prediction algorithm is then built upon both data, but also I showed a slide earlier, I think before you joined, that slide goes into various theories of motion sickness. So using those theories, we're building certain models that, let me see if I can get to that. Right here.
Oh, okay.
That, based on the kind of motion that you subjected to, can one predict? I mean, these theories lead to models. Can these models predict how much motion sickness is going to happen? So that is a sort of secondary or another part of the project that we're working on.
Great, thank you. Can I ask one more question? So the second question is, you said you guys are going to start doing some MCD testing.
That's right.
With real subjects. So I'm a little bit not clear, how will you judge the result? Because here you have to have those actual drivers have motion sickness, and then they have to experience motion sickness. So how are you making them experience motion sickness? Because not everybody, if going in the car just some turns, is going to experience motion sickness.
Exactly. A very valid question, and that's sort of the challenge of human subject experiments. So we are planning what's called a within study, and within study means that there's a control condition. So, we're going by the metric that 1 in 3 people are prone to motion sickness. And we, for example, are recruiting 30 people. And the statistical expectation is that at least 10 of them will be prone to motion sickness. So each person will be driven around on that MCT path that I showed. That is a motion sickness inducing path based on previous studies we know because of so many start, stop, and left and right turns. So at least 10 of those people should demonstrate signs of motion sickness. And that is, there's a self-reported motion sickness score where we have already trained them ahead of time what 0 means, what 10 means. And there's also a qualitative score. There is also not just asking them, for example, measuring their heart rate, their perspiration level, their body temperature, which are all correlated to level of discomfort. So that's how we're monitoring, and we will show that under control condition, perhaps 10 people are motion sick. Now, the efficacy of this would be, at least for those 10 people, once we turn on PREACT, can you... Exactly. So that's the study. Exactly. Yeah.
Thank you.
You're welcome. Yeah. I think there was a question in the back. Oh.
Hi. Thank you very much for the presentation. My main question...
Can I ask your name? I'm sorry.
Oh, yes. My name is Agamanakta from the University of Illinois.
Illinois. Awesome. Urban.
PhD candidate, yes.
Okay.
You said that, I guess the theory is that the driver kind of knows that a turn or a stop is coming. So the reason I kind of paused, because I get like motion sickness as a passenger, and I still know that we're stopping because I see the light, and I see that we're turning because I hear the signal. So how proven is it that the reason why there is motion sickness is because I know I'm turning, so I kind of lean into it?
Right. It's a very good question. Your question goes to the heart of the strength of anticipation and the strength of preemption. Now, I'd say going back 30 years, there are experimental studies that demonstrate over and over that even though the front seat passenger has some idea of what's going to happen, their level of preemption is not the same as the driver. their level of preemption is not. In fact, the driver, for example, will turn on if you're an annoying driver like me, I turn on the right indicator like 2 minutes ahead of time, and my family complains, what the heck, right? If you're a passenger, then you don't know when is this guy going to turn, right? Versus as a driver, I know exactly when I'm going to turn, right? So that level of, or the strength of my prediction, my anticipation is stronger than the passenger. Similarly, the strength of my preemption, if, for example, I'm driving, I know what my mood is, and I might be in an aggressive driving mood. And in an aggressive driving mood, I might take a sharp right turn, but because I know all of this, I'm going to lean my body hard into the turn. While my passenger perhaps knows that I'm going to take a right turn, but they don't know when I'm going to take a right turn and how hard that's going to be. And therefore, that strength is not matched. And again, all the theory, all the experiments do demonstrate a distinction between the driver and passenger, their motion sickness level. All these studies also have measured the body movement, right? So there's a very famous study by a researcher, Wada, at some institution in Japan, where they have literally just measured the head tilt. And while taking a turn, consistently they show that even like slightly before the turn has happened, the driver tilts their head into the turn while the passenger is still wobbling around. I mean, they try to fix the thing like in real time, and it's delayed a little bit, and that leads to a worse outcome. You're welcome. Here, yeah.
So this is Brian from PREACT.
PREACT?
Yes.
Okay.
So I think, very interesting study. So I think there is some big overlap between one of the study we've done about 2 to 3 years ago.
Okay.
That we also collected like drivers' motion sickness through their subjective scores.
Right. And
also,
by the way, we're using the same scores, that...
Yeah.
Right? It's the same that you have developed.
Yeah, from the 0 to 10.
0 to 10.
Yes,
you are with Monica Jones's team?
Yes.
Right.
Yeah.
So we're using that. From your publications, we're using that.
Right. So one challenge we're facing was kind of, it's very difficult for us to predict using the physiological data to predict the motion sickness. Well, the reason is some human subjects are kind of hugely affected by their susceptibility. So some people, they got sick after 3 seconds on roll. Some people never, even they look at the iPad.
Yes.
So, but their physiological data looks exactly the same. So, but they're just like, it could be the age issue. It could be just a, individual difference. Some people just feel sick very easily. So, I know you haven't run the human subject study yet, and it could be an issue. Let's, once you started working.
Yeah. In fact, we anticipated that to be a big issue just because of the incredible amount of variability from one human to another human. So while I would say we're in the first stages of our studies, the solution that I anticipate and that we have proposed is one where we want it to be highly customized to the individual. So what I showed in this slide here, when I talk about the passenger state, right? That passenger state, I know this is from a privacy standpoint a little bit of an invasive issue, but I'd like to imagine a scenario that you enter a vehicle and you sit on could be anyone's vehicle, and there's a bunch of seats there. They're all PREACT equipped, but they recognize who you are. Right? Your ID is recognized. And the moment your ID is recognized, then the secret sauce, so what combination of active seat, active restraint, active this and that, and the degree of preemption, the dosage of preemption is customized to your needs. And every time you ride a vehicle, every time the system collects that data so that incrementally, after 4 or 5, it's a learning algorithm that it tunes itself to your liking. I know this is sort of a sort of future thought, but I do strongly believe that the solution has to be customized to the individual, and this platform supports that.
Yeah, I think that's kind of that's reasonable. And one thing we also, like when we ran a study 2 years ago, we have the that's the human subject is served as a passenger. So we have the other drivers to control the vehicle. So we cannot guarantee all the profiles for on the loop will be the same.
Yeah.
So what we're doing right now is we have another MCD projects, and we try to use the automated vehicle. Yeah, to make sure all the profiles
Highly repeatable.
Yes, for every subject to be the same.
Yeah.
So we're trying to understand if that some of the effect could be reduced.
Yeah.
And to make sure that that could be.
The way we're doing it, we're just training the heck out of our drivers. I mean, we have, so Nishant is running these studies, and he's training drivers to do the exact same loop over and over and over again. Anyway, thanks a lot for all the feedback.
So let's give Professor Awtar a round of applause. Thank you for your time, Professor.
Thank you.
So now we're going to go on break for about 10 minutes, but at 2 o'clock, you can join us back in the Rogel. We're going to have a keynote speech from Director Shelby Skeels from the Office of Small and Disadvantaged Business Utilization at the USDOT. Thank you.